I'm presenting a question about scikit-learn's kernel approximation tool and its use of the SkewedChi2Sampler. We'll explore how the skewness parameter impacts the feature map it creates. Think of it like adjusting a camera lens. We're altering how the data is viewed. This question focuses on the kernel approximation function in scikit-learn, specifically how the SkewedChi2Sampler and its skewness parameter affect the data transformation. I want you to think critically about how this parameter influences the final output, the feature map. This statement explores whether cranking up the skewness value improves the approximation accuracy. I'm not sure it always does. It might for highly skewed data, but could also overfit or cause inaccuracy in less skewed data. Let's consider the situation holistically. Here, I am asking you to think about the processing power needed. Increasing the skewness value doesn't significantly increase the calculation time. It primarily depends on your data size, not this parameter. Setting skewness to 0 essentially turns off the skewness correction. This means you'll get a regular chi-squared sampling, a standard approach. A higher skewness value puts more focus on larger data points. This is precisely what this parameter does. It counteracts the skewness effect by prioritizing larger values. This is a specific function in scikit-learn designed to deal with datasets where features show a skewed distribution. Think of it as a special tool to handle messy data. This is the key control in SkewedChi2Sampler. It's a number that lets you adjust the emphasis placed on larger values in your data. It's like a dial to fine-tune your transformation. I see that you're focusing on the SkewedChi2Sampler. This is a crucial part of scikit-learn's kernel approximation technique. It's designed to handle datasets where the features are highly skewed, meaning that some features have many more values concentrated on one side of the average than the other. The sampler will attempt to reduce the effect of these skewed features. The feature map is the output of the kernel approximation process after it has applied the SkewedChi2Sampler. Think of it like a transformation of the original data where each data point gets mapped to a new set of features. The purpose of this transformation is to improve the performance of algorithms that are sensitive to how input data is distributed, particularly when working with skewed data. This statement tells us that if we set the skewness parameter to 0, the SkewedChi2Sampler essentially behaves like a standard chi-squared sampler. It means no special adjustments are made to account for skewed features. I'm going to emphasize the key takeaway here. A higher skewness value makes the algorithm pay more attention to the data points with larger feature values. This is important because it's the algorithm's way of correcting the influence of highly skewed data. This sets the scene. We are dealing with a machine learning problem where we are using a specific technique, kernel approximation, with SkewedChi2Sampler, to deal with data that has an uneven distribution of values in some of its features. This simply indicates that what follows is a multiple-choice quiz question testing the understanding of the concepts previously explained. This question tests your understanding of how the SkewedChi2 parameter in scikit-learn's SkewedChi2Sampler affects the transformation of data and the resulting approximate kernel map. It's all about understanding the impact of this parameter, not about doing complex calculations. I'd say this statement is partially true, but not universally. Increasing SkewedChi2 might improve accuracy for very skewed data, but it could also lead to overfitting, modeling the training data too closely, or inaccuracies with less skewed data. The best SkewedChi2 value depends entirely on the specific data. This is mostly false. The main factors affecting computation time are the number of features and data points, not the SkewedChi2 parameter. Any increase in computation due to a higher SkewedChi2 value is usually negligible. This is absolutely correct. A SkewedChi2 of 0 means there's no adjustment for skewness. It's just a standard chi-squared sampling. That's spot on. The whole point of the SkewedChi2 parameter is to give more weight to larger feature values, which helps counteract the effects of skewed data. I'm using scikit-learn's kernel approximation, a technique to approximate complex kernel functions. It's particularly helpful when you have lots of data and calculating the exact kernel is too slow. I'm using it with a SkewedChi2Sampler, which is a specific method designed for datasets where features have uneven distributions, they're skewed. This is a multiple-choice quiz testing my understanding of how the skewness parameter affects the feature transformation using kernel approximation in SkewedChi2Sampler. These are the multiple-choice answers I need to evaluate based on my knowledge of how the skewness parameter in SkewedChi2Sampler works with the kernel approximation algorithm. I need to determine which statements accurately reflect its effect on the feature map, the transformed data. This sets the scene. I'm working with a dataset that has some features with very uneven distributions, lots of small values, a few large ones. I'm using kernel approximation to speed up calculations. I'm particularly interested in understanding the effect of the skewness parameter. Increasing the skewness parameter might improve accuracy for very skewed data, but it's not a guaranteed improvement. It could even hurt accuracy if the data isn't that skewed, or cause overfitting. The ideal skewness value depends heavily on the specific data. This statement is generally false. The main computational cost comes from the number of features and samples, not the skewness itself. Any extra cost from increasing the skewness is usually minimal. This is absolutely correct. The whole point of the skewness parameter is to give more importance to those larger values. It's designed to counteract the effect of skewed data. I understand that. This statement is true. A skewnes value of 0 means you're not adjusting for any skewness in your data, so you're just doing a regular chi-squared sampling. Think of it as the baseline. No special emphasis on any feature values. This is absolutely correct. That's the main point of using the skewness parameter. By increasing the skewnes value, you tell the algorithm to pay more attention to data points with larger feature values. It helps counteract the effect of skewed data, where a few large values can disproportionately influence your analysis. I see this statement as generally false. The computational cost is primarily determined by the size of your dataset, number of features and samples, and not directly affected by the skewnes parameter itself. Any increase in computation due to higher skewnes is usually negligible in comparison to the overall computation time of the transformation. I would say this isn't always true. While it might be helpful for highly skewed data, you could overfit your model or get a less accurate representation for data that's not that skewed. The best value for skewnes depends entirely on your dataset. This is the core question we're trying to answer. We're exploring how changing the skewnes parameter in scikit-learn's SkewedChi2Sampler affects the results you get when you transform your data using it. These are the multiple choice options to assess your understanding of the skewness parameter within scikit-learn's SkewedChi2Sampler. Let's examine each one carefully. I'd say this statement is generally false. The main computational cost comes from the number of data points and features, not the skewness value itself. Any increase in computation due to a higher skewness value would be minimal. This is absolutely correct. Setting skewness to 0 effectively disables the skewness adjustment in the SkewedChi2Sampler resulting in the standard chi-squared sampling method. I wouldn't say this is universally true. While a higher skewness might indeed improve accuracy when dealing with truly skewed data, it could potentially lead to overfitting or even reduce accuracy if your data isn't highly skewed. The ideal skewness value really depends on your specific dataset. That's precisely the point. The whole purpose of the skewness parameter is to give more weight to larger features. This is especially helpful when your data has a skewed distribution, as it helps counteract the influence of those long tails in the distribution. This question focuses on how changing the skewness parameter in the SkewedChi2Sampler affects the way your data is transformed and how accurately it represents the original data. I'll break down what skewness does and how it changes the results. If you set skewness to 0, the SkewedChi2Sampler acts like a standard chi-squared sampler. Think of it like turning off a special feature. You're just getting the basic chi-squared transformation. A higher skewness value means the transformation will pay more attention to features with large values. It's like using a magnifying glass. Those big values get boosted more. Increasing the skewness parameter doesn't significantly increase the computation time. It's the size of your data, number of features and samples, that mostly matters for the calculation time, not the skewness itself. Increasing skewness doesn't automatically guarantee a more accurate representation. The best skewness value depends on your data. Sometimes it helps, sometimes it doesn't. It's trial and error situation.